So we started with an example for rotation of the plane on the ring. So here is the model. The model says, okay, it is a free particle moving on a two-dimensional plane, but we constrain the radius as a constant. All right. So we take an example for the xy plane as an example, and we went through from the quantum mechanics point of view, how we can generate the Hamiltonian operator, plug it into the Schrodinger equation. And I remember we ended coming up the general solution for the Schrodinger equation, but we ended at the boundary condition. So I'm just flashing through my notes, which we went through on the chalkboard. So it's a two-dimensional problem. So therefore, you have one particle moving on an xy plane, so you will have xy variables. However, because we constrained the radius is a constant, so you reduce your variable from a 2 to 1. All right, and then we use the spherical or cylindrical coordinates. Instead of xy, we use the r and phi. So here is your Hamiltonian operator, and you plug it into the Schrodinger equation. Only the phi is a variable because we fixed the radius. And then we're solving for the Schrodinger equation. So the general solution for the wave function is only carries one variable, as I mentioned, two-dimension, reduced one, so only depends on the phi. And then it's an E function. It's a complex function, as you can tell, carry the I right here, and times m sub L. M sub L is usually your quantum number for rotational motion. Then carry your variable for the position. We use the phi to indicate. So that is your general solution. All right, now this is another normalized function. So we know for the phi, it's between 0 to 2 pi. Okay, so mathematically, that is a solution. However, we need to apply it to our system. Since you rotate on the plane, so at any point of the phi, you add 2 pi, the wave function has to return to the same value. So your boundary condition would be the wave function at any phi value would be the same for the phi at one revolution. So that is your boundary condition. All right. In that case, we can substitute the phi, all phi plus 2 pi, into your wave function and set them equal, and that's what we ended here. Here's the solution. In order to make that true, then what we need to derive is the E raised to the 2 pi m sub L and I has to be equals to 1. All right. Maybe I should just use the slides upstairs. It posted on the slide right there. So in order to satisfy this boundary condition, then this has to be true. Now we know this, you can rewrite this as e to the I pi raised to the power of 2 m sub L. All right, that's just a relationship that you learn from the E function. Okay, and that has to be equal to 1. Now we know using the formula, E to the I pi equals to cosine pi times I sine pi. Right? That is a very important formula you want to know. Okay, now we know sine pi equal to 0. Okay, cosine pi equal to -1. So therefore, e raised to the I pi equals to -1. Any questions on this? Okay, now if we plug it in here, if we look at this, e raised to the I pi, that is equals to a constant. So you plug in -1 raised to m sub l. So therefore, for this to be true and equals to 1, then what has to be true? Then if this has to be true, this is already 2 times some numbers as long as m sub l and integers. This expression would be true. Okay, now that's how we can derive the m sub l in this wave function expression equals to integers. Integers can be any integers from negative value to the positive value, so we can rewrite okay, all right. Okay, does that make sense? So we know our model, we generate Hamiltonian operator, we plug into the Schrödinger equation, mathematically we solve for that solution, we have a general solution. But then we need to impose the boundary condition. Here is a cyclic condition that the position at any angle will be the return to the same if you have any integer number of a revolution. And based on that, we can constrain the value for m sub l. So here we go. That is through the boundary condition, we derive the m sub l has to be integers. So from negative to 0 to positive. All right, so this tells you, again, similar to the translational motion, vibrational motion, the system is in a series of rotational quantum states. All right, now, so the system in a series of quantum states, how do we know? That quantum state is determined by the m sub l value. M sub l equal to 0, you have one quantum state, one mathematical expression, m sub l equals plus minus 1, then you have various. So this tells you the system is in a series of quantum states that is denoted by your rotational quantum number m sub l. Okay, all right. All right, so we complete our discussion for the wave function. Okay, now, I'm not going to show this, I'm going to better work through with on the board. Now we have a wave function, have a quantum number that is determined, but we need to make sure for a complete wave function, we need to make sure the wave function is normalized. So now how to normalize a wave function is by introduce a normalization constant to whatever the wave function of our interest, right? So you need to introduce a normalization constant multiplied by that function. Then what we do is we do a complex conjugate of that wave function multiplied by that wave function itself, and then you integrate with the allowed space. In this case, the allowed space is only d phi. Okay, so this is the complex conjugated wave function multiplied by the wave function itself, integrates through the allow the space. This is only have one variable. It only depends on the angle of the phi. And then what you need to do, you need to put the right limits or the boundary here. So for the phi variable, guys, what should we leave it here?
0.
0
Pi.
to pi. Okay. All right. Now let's give it a shot. Okay. So in that case, what we have in here is you will have 0 to 2 pi, and then you have your wave function. I'll check out the m is a real constant. Or we can do this, only a real constant, and then you'll have a complex conjugate of the wave function, non-normalized form. Okay, and then you multiply the constant itself. Alright, this is your wave function times the normalization constant, and you take a complex conjugate. Okay, alright, now this is a complex function. How do you know? Because I have a I right here. So take out the complex conjugate operation. What do we have, guys? This, if I do operation, what I'm gonna have? I'm gonna flip the sign. Okay, very good. And then I have a E and the E function. It's a E raised to the A times E raised to the B that equals E raised to the A plus B. Okay, so between these two, what do we have, guys?
E to the 0.
You will get an E to the 0 order, and that will equals to 1. Okay. All right, so therefore, this really equal to the 0 of 2 pi, and that's a real number, we know. Then n, or we can make it n squared, and d phi. So that will give you n squared. If you take out the integral with respect to d phi, what do we have? Phi is your variable. You can think about this as really your 1 right here. So what do you have? Just phi, right? Okay, so then this equals n squared times phi, which value is from what?
0 to 2 pi.
Alright, and then what you have is n squared times 2 pi minus 0. If it's a normalized, what do you have? Normalization means this integral equals to 1. True? Okay. All right. Then what does that tell you? So this is equal to 1 because of a normalization. Right? Because this is your probability density times volume, probability at one location, integration over all allowed space, that's a total probability. Total probability equals to 1. Okay, in that case, what do you have for n here?
The square root of 1 over 2 pi.
Right? Now, mathematically, you would add what? Plus minus. But do you think an amplitude with a plus minus make any differences in quantum mechanics? No, because we don't care about the amplitude. We care about the square modulus, which you plus minus cancel. It doesn't matter, they are exactly the same. So therefore, we will only take the positive value. So in that regard, this is the complete wave function for rotational on the ring, and as a normalization constant is a key function. Yes?
Why do you have to normalize for this function?
What do I want?
Why do you have to normalize this function?
Because, oh, what do you guys think? Why do you have to normalize the function?
To make sure your total probability is 1.
Exactly. So when you want to know the probability, a particular range of a phi, then you get to the 1 value. Okay, so exactly, very good. Okay, all right, so that is your complete wave function. Now, once we know the wave function in quantum mechanics, we are golden for so many things because we can predict different things, right? We can predict the properties by knowing the operator operate onto the wave function. We can predict the values, right? So that is the whole foundation of the quantum mechanics. Is everything is carried in the expression of the wave function. Once we know it, we use the operator and predict the values. Okay. All right. So the big question is, how can we determine the observables? For instance, your potential energy, in this case potential energy is 0, your kinetic energy values, your total energy, your linear momentum, your position, right, and your angular momentum. For instance, we can predict position, I can write some linear momentum, right? Angular momentum and energies, right? Those are the things that we're interested in. Since the system is rotating, we want to know what is the energy associated with that. Now, how about, since this is rotational motion, we are very interested in angular momentum. Now, how can we predict angular momentum? Or how can we generally approach this problem? Right? We're interested, want to know observable, a particular observable of interest. What do we need to do?
The operator.
We need to generate an operator. Okay. Now, if I would like to know the angular momentum in physics, we use a J as a notation for angular momentum. Now, angular momentum here have a component of Jx, Jy, and Jz. Have different component in the X, Y, Z component. Now, for this case, our total angular momentum. Do we have an XY component for angular momentum? Right? Do we have? So we rotate on the XY plane. Remember the picture I showed you? Here we go. So if you look at, yes, in general, you have a system in a three-dimensional rotation, you will have an X, Y, Z component, same as your linear momentum and kinetic energy. But in this case, you can look at this diagram showing you the J is really the cross product of the radius and your linear momentum, okay? And you rotate on the fixed plane, so it's a cross product. And if you use a right-hand rule based on your position and your linear momentum, the angular momentum only resides in the Z component. So therefore, if I'm asking the angular momentum for rotational on the plane, then you only have the Z component, so therefore the total is equals to the angular momentum in the Z. Now that is not true when you have a rotation of the three dimensions. For this case, the total angular momentum is the same as your angular momentum in the Z axis, because that's the only angular momentum direction you have. You guys all clear on this? Okay. Now, if I want to calculate the angular momentum, this is on a, let me write it, please, so we know on the xy plane, you just calculate the z component. Now, we want to know the J. Now we're really reduced to how we're going to calculate the J sub the z. So we need to generate the operator for that angular momentum in the z-axis. Okay, now what is the operator for the angular momentum in the z-axis? We can use an xy as your variables, but we can also use cylindrical or spherical coordinates. And if we know the relationship between xy versus r phi, for the z component, the angular momentum can be written as h bar over I, then the derivative with respect to your doesn't this look very similar in the format than your linear momentum, guys? So what is your, let me write it here. What is your linear momentum operator? Is a h bar over I constant? Then what you have is derivative with respect to that position axis. Now, if it's a z, will be dz. If it's x, will be dx here. If it's a y, will be dy here. Now, if for the angular momentum in the z component, if we use r phi as a variable, it has similar format. It's in a constant, then your derivative with respect to your position variable, which is your phi here, because you're using the spherical coordinates. Now, what you're going to be extrapolate to the angular momentum in the x and y, I'm going to leave you guys go home and try it out. But for the z component, it is easier to remember because they carry the same fashion. Okay, if we know the operator, that's good. Now, how to predict? One way to predict is you have this operator. So you could have the operator operate onto the wave function. If that return to you a real constant multiplied by your original wave function, then that real constant is the predicted observable values. Okay, now let's see if the wave function is an eigenfunction for your angular momentum operator. So let's plug it in. We have h bar of I, your wave function, carry the constant, then the E. Ooh. Forgot about the derivative. Okay, so all I did is I have an operator operate onto the wave function. Okay, now this is a constant. Take out the derivative. All right, now what will be the derivative for the E function? It will be itself, right, first. And then you use a chain rule with respect to the I epsilon phi, which give us
M's by.
yes, it's awfully higher, making me think today is Friday. so I wasn't sure what day is today. Yeah, you guys all follow me, okay? Constant out of the derivative with the e function to the e itself. Then you can look at evaluate it here. If there's anything further here, we need to use the chain rule. Now what do we have? Okay, so I have I in the denominator that will vanish to 1. And then what I have here is h bar m sub l. Then I have this constant. I have this e function. So is this rotational plane wave function an eigenfunction for angular momentum?
Yes.
Very good. Because this is the original wave function. Okay. All right. Now, what is the eigenvalue? What is the eigenvalue?
H bar.
So the eigenvalue, which means I can write out J equals to the component in the Z that give you value m sub l h bar. Okay, now m sub l is a quantum number, so m sub l equal to 0. Right, so it depends on the quantum state. I will have a different values for the angular momentum. Okay, now previously we talked about, for the translational motion, vibrational motion, we say the system in a different quantum state with associated energy. The energy are quantized. Quantized means they are not continuous. They're confined to discrete values. For the rotational motion, the angular momentum value also is discrete. It's not continuous. So we can also say the angular momentum is also quantized. You guys follow me, okay? All right, now you can have a different values. If I tell you at what particular state, and you get the value. Now, what if the m sub l equals to 0? When m sub l equals to 0,
It doesn't have anything
then your j equals to 0. So your angular momentum is 0. All right. Okay. All right. Okay. This is what we just mentioned. The values and quantization of the angular momentum. That's really under the category of how we're going to define, how to determine an observable. Here, the observable associated with a rotational motion is your angular momentum. And we just derived that the angular momentum value is m sub l h bar. And when m sub l equal to 0, then the particle is at stationary. Okay. Now, how about the position? How do we understand the position of the system? Right? We said the significance of the wave function is not in itself. It resides in the probability density, because from the probability density give us information about the probability to locate that particle. Okay, now applying to the rotational motion. So what would it be the probability density? What would that be equal to? So you take a complex conjugate of your wave function, right? I think plug in if you want me to, but I thought at this point that it is is your probability density. Yes. All right, and then this E and this E function will give us
0 to 1.
E sub 0 will give us to 1. So therefore, your probability density for the particle rotation on the plane equals to the constant. So that doesn't depend on the position. So now if you look at the angular momentum and the position, you can see this is a pair of complementary observables. Okay, you can precisely determine the angular momentum. However, you lost the determination with precision for your position, because this has an equal probability at any parts of the plane. However, your angular momentum can be precisely determined. Right? Okay, now we can prove that. I mean, I'm showing you here by plugging in a corresponding to and showing, but we also can prove it. How can we prove a pair of observables that are complementary? How do we do it?
If they do not commute.
So we need to evaluate commutator, right? We need to evaluate the commutator. Okay, now I'm wondering which part I should write on this one. Let's see. We say if a pair of observables they are complementary, then we evaluate the commutator operator for those two operators. If they are complementary, this value equals to, if they are complementary,
0, right?
if they're complementary, it would not equal to 0. Oh, it's confusing, isn't it? Because if they're complementary or if they are commuting, right? If they commute, they are not complementary. Okay, it's a little bit confusing. So let me write it out. If they are complementary, then those two do not commute. If they do not commute, they do not equal to 0. Okay, if they commute, they equals to 0, this value. Alrighty, now we'll evaluate those two operators. One is your angular momentum, and the other one is your position. Now position here is we're using the spherical coordinates, so your position is really your phi, that's your position. So we evaluate the position phi versus the angular momentum operator. Okay, now how we're going to evaluate this commutator is we have to apply this to the wave function and then get the value. All right, so I think I write it out here already. So if you take a look at this one, to evaluate the commutator, which really switch the order of the operation sequence and then get what you want. So the first we evaluate operating the position first, followed by the angular momentum. And do you want me to go through it, or looking at the slide is okay? Which one you want to go through it, or just look at the slide?
Go through it, please.
Huh?
Go through it, please.
Go through the board? Sorry?
On the board.
On the board? Okay. Yeah, we can do that. All right, so let's evaluate the on function. Okay, all right, now let's plug in the expression for your operator. So in operator, the closest means first. Then the outcome of this, then you have the operation for your second operator. Okay, let's get this sorted out correctly. So then we have the angular momentum, that is your operator, operate onto the outcome of your position operator onto the wave function. The position operator is just a variable multiply. Now the variable for position for the rotational motion is just the phi right here. You guys all follow me okay here? Okay, and then you have the wave function. Okay, now you're going to carry the operation from your angular momentum, which is the derivative with respect to your position phi. What rule are we going to apply here?
Product rule.
This carries the variable. This also carries the variable. So what rule do we use? Product rule, right? Do you guys follow me okay? So then we will have a constant. The product rule tells us you have the derivative on the first one. So that which means you have a d phi over d phi times the second wave function, second function by itself. And then you're going to have the first by itself, then you do a derivative with respect to the second function. That's the product. Can you guys see it at the end? Okay, so now d phi over d phi, that'll vanish to 1. Yes? And that's all you have. There's not much I can do about this. Okay, right. Now let's switch the order, which means I will have this first, and then have the angular momentum operator. That is the value of the commutator, is to see the differences of outcome if I switch the order of operation for those two operators. Okay, now again, this is a position operator. It's just a variable for that position, multiply. Okay, now you have the angular momentum operator, which is this, and then it's a derivative with respect to your position, and then operate onto your wave function. Any questions on that? And there's not much I can do about it. I have to end it here. Now I have these two sequences. So what would be the difference between the two? So if I write out the whole evaluation, because the commutator is really to evaluate right, the differences. Now I have the differences. So what I'm going to get, this, what I have is for the first, for the position first and the angular momentum, that's what I have. If I switch the order, if I do the minus between these two, what do I have? I have this guy, the h bar over I, phi, d phi over dc over d phi. That is exactly the same here. So I cancel one term. What really remains is h bar over I. Is that a 0? Do they commute?
No.
They do not commute. If it's a 0, these two operators, they commute. They do not commute. Therefore, they are complementary observables. If they are complementary observables, then they are an example for the Heisenberg uncertainty principle. Means either one of them. You can't determine with certain precision for those two simultaneously. So far, we learned the linear momentum and the position, they are complementary. Now the angular momentum and the position, they are also complementary too. Okay. All right. Okay. All right. Very good. Now we say you have a wave function. You can determine the observables. I'll show you for the angular momentum as one example. The other important observable is the energy. Now, in quantum mechanics, how do we obtain values for energy?
Using the Schrodinger's equation.
How do you do it? Yeah, so basically, you have the Schrodinger equation. Once we know the solution for the wave function, we plug the wave function expression into the Schrodinger equation, and then work on the Schrodinger equation, and that's going to give us the energy values. Alrighty, now you guys can try, plug it in, because the Hamiltonian operator operate onto the wave function is really give us the energy for the system. So it's the same as we are doing for determining the angular momentum. Okay, that's how we determine the energy for the rotational motion on the plane, and the value is, so let me write it here. By doing that, the energy also carries the quantum number to denote the energy associated with the different quantum states. So the expression equals to quantum number m sub L squared times h bar squared over 2I. Should I write it here out here? So that E m sub L squared h bar squared over 2I. Now I mentioned in the rotational motion, I said, what is I here? Capital I, guys? Huh? Is the moment of inertia. So you have the particle with a mass of m, and then you rotate on the xy plane with the radius of r. Then m times the r squared, mass of the particle, times the radius squared, that is the moment of inertia. Now, for sure, you can carry the mr squared here as you wish, but this makes the expression a bit simpler. That's about it. Okay. Now, this is an expression. I told you how we obtain this expression. Now, is this energy quantized? It is quantized. It's not continuous. How do I know? Because it's confined by your quantum number m sub L. M sub L only can take integer value. So therefore, the energy of this rotational system is also quantized. Now, what is the ground state energy? Okay, so remember guys, when we say the ground state, what is ground state? It's the state that has the
Lowest
lowest
energy.
energy. Okay, now if I evaluate this expression, I is a constant for the particular system, mass is known, radius is known. H bar, of course, a constant. So varies, your energy varies directly with your quantum number, or specifically to the square of the quantum number. And then you evaluate the quantum number takes integer values, so you know the lowest will be referred to when the m sub r equals 0. Okay, and then your energy equals to 0. So there's no 0 point energy. This is also we call it 0 point energy. The ground state okay. Now, what is the expression for the wave function for the system at the ground state? For the system at the ground state is when the m sub r equals Did you just mumble when I turn my face around and just trick me?
So it'd just be the normalization.
So when the system at the ground state, which means the m sub l is at 0, because the ground state is your lowest energy state, right? So when m sub l equals to 0, what is our wave function expression?
The square root of 1 over 2.
So then that's your general expression that represents all the possible rotational quantum states. Now we know specifically for the ground state, the energy of the m sub r equal to 0, and then we directly plug in. Wave function C has one variable defined by the quantum number. The quantum number for the ground state is 0. So if I plug in, what do I have? That is your wave function for the ground state. Okay, now what would it be for the first excited state? Let's say when m sub l equals plus minus 1. That's your next higher level for the energy. Do you guys agree? The next higher energy value is when m sub l takes plus minus 1. Okay, now the energy value when m sub l equal to 1 is the same as m sub l equal to negative 1, because in the expression it is a square of m sub l value. So plus minus makes no difference. What would be the value for the energy?
H bar squared over 2i.
H bar squared over 2i. I didn't do anything fancy, I'll just do it as ink. Now, how about wave function? Then you have wave function m sub l equal to 1. I just plug in the corresponding quantum number. wave functions corresponding to one energy value. That brings up to a terminology we learned, what is it? Degeneracy. So in this case, you have two energy values, two quantum states refer to one energy values. That is your doubly degenerated, except at the ground state. At the ground state, you don't have a degeneracy, or your degeneracy value is just equals to 1. Now, what do you tell about this plus minus E function? That actually indicates the rotational direction. One is the clockwise with a positive and some up. Now, negative I, it rotates in a counterclockwise direction. So the plus minus indicate the differences in the rotational direction. Okay,